decided to tell you tonight about gravitational waves, what we have discovered, and how we are hoping to use it to explore the universe. So let's see if this works. No, it doesn't. Okay. All right, I can do this. So if you go outside on a very clear night, away from the lights of the city, and your eyes are super, super sharp, you could see an image like this one. Actually, this I'm cheating because it's an image from the Hubble telescope. It's a deep field image. And it shows, you see structures over there, maybe a few more than I was expecting because of the waves on the screen. So those structures are galaxies, there are stars. These are all informations that we know about the universe from various forms of light. So everything we know about the universe up until 2 years ago was coming from electromagnetic waves at different frequencies. So visible lights, infrareds, ultraviolets, gamma, X. And that's how we put together all we know about the puzzle that is the universe. And so a lot has happened since Galileo first pointed his telescope to the skies 400 years ago. And we understand a lot about it. It's not just a set of stars that are there waiting in a nice constellation. It's actually a very violent environment where galaxies collide, stars explode. We thought there were black holes, actually we knew there were black holes like at the center of the galaxy, but still there still are lots of unknowns. Like we only know what's about 5% of what composes the mass of the universe. So what is dark matters? What are these black holes? How do they form? What happened in the first instance after the Big Bang? So there is still a lot to discover about the universe. So the glue that keeps the universe together is gravity. So gravity explains why planets move around stars, the stars move in the galaxies collide, and that has got us going for many years. However, Einstein was not happy with this picture of gravity, and so he basically reinvented gravity as a pure geometrical property of space. So he didn't like the idea of a mysterious force between two objects. So instead he re-explained gravity as the motion on a curved space. So this is a two-dimensional representation of space. And what you see, those objects in there are planets or neutron stars. What they do is that they bend space. And so the reason why Earth is moving around the sun is not because there is a mysterious force attracting it to the sun, but because the sun is moving on a curved space, a little bit like those coin tossers. Do you ever put the coin on those funnels and then the coin goes down? So that's what a black hole is in general relativity. A black hole is a funnel in the fabric of space, or space-time if you make it more complicated. Okay, so this is the new picture of the universe with the eyes of Einstein. There is a little funnel back there. Again, this is not really working for me, or I would point it. There is a little, I don't know if you see it back there, that funnel, that's a black hole in that picture, okay? So, gravitational waves were, oh, here's my tech help, thank you. So, gravitational waves were introduced by Einstein 100 years ago, actually 102 now, this slide is a little bit old. As part of the theory of general relativity, and he introduced it as these ripples in the fabric of space. Remember that undulated structure, there is a two-dimensional universe? Well, if something happens, and for instance, oh my gosh, what's happening here? Okay, it's moving for me, thank you. All right, so you already got my punchline there. So if, okay, so I'll just move here. So if these dense objects, like black holes, neutron stars, I'll tell you much more about neutron stars later, they move, they change the way they disturb the fabric of space-time. And so this change propagates like a wave. Just like if you take a stone, you throw it in a pond, they make ripples that propagate. The same thing happens to space-time. So this little movie shows, let's see, these two white objects, these are, imagine those as being two neutron stars, two dense objects, two black holes, and they rotate around each other. As they do, they change the way they modify space, and here's these waves are the gravitational waves that are propagating away from the source. And now, if you fix your attention on any 2 points on this grid, you will see that as the wave goes by, they get a little bit closer, a little bit farther away. So the gravitational wave does this to space. It stretches, it squeezes it, it modifies it. So again, general relativity is the geometry of space-time, and the wave, the gravitational wave, is the perturbation of space-time. And so if something happens out there, the wave comes and tells us, traveling at the speed of light, what happens in the distant, at a big distance or in the distance past. So why do we care about detecting these gravitational waves? Well, the way I like to describe gravitational wave is it's a new sense. It's a new way to probe the universe. Okay? So imagine, just let's look, indulge me and watch this little animation for a little bit. Imagine this is a silent movie of the jungle. So you look at it, and you see there are leaves, there are trees, there are waterfalls, there is stuff going on. However, imagine turning on the sound to this movie. And now you see things you didn't know about before. So there are monkeys in there. There are animals, there are birds, and then there is lots of energy in that waterfall. You can hear it, it's rumbling. And then you may find surprises. There it is. So, going after gravitational wave, it's a little bit like turning on the sound on the universe. We get a different type of information. It's just the same as you see, you hear, your brain puts the two things together, and then you get a whole new perception of reality. So that's what we're trying to do by detecting gravitational waves. Because gravitational waves tell us things that we cannot see. It's not light, it's what happens when heavy objects move and smash. And so we can learn about black holes, and maybe at some point we can learn about the first instance after the Big Bang. So there is a lot we can explore with the gravitational waves. So I hope I convinced you that it's a worthwhile endeavor to detect gravitational waves. Yes? Please? Yes? Good. All right. So let me tell you the story of the first gravitational waves that we detected. Okay? So 1.3 billion years ago, there were two black holes. They were about 30, 40 times the mass of the sun. And they, in spirals, they were getting closer and closer, emanating gravitational wave. As they got closer, they went faster, emits more gravitational wave, up until the moment they collided. Now, I'm going to go back and replay this for you. What you see here is not light that's produced by the emerging black holes. No light was produced there. The two black holes are called black holes because they're black. They don't emanate lights. We don't get any spark of light coming out. This is a simulation that's slowed down by many factors. And what you see here is the light that was from the stars behind the black hole that's deviated by the black holes that move. And no telescope is as powerful as to show this one. Okay, so where the energy is produced, what we can get out as a signal from that event is the gravitational wave. And so this is a simulation of the two black holes. It's a numerical simulation, so we take the equations of Einstein geometry, put it on supercomputers, and calculate the trajectory of these two black holes up until the moment they merge. Most energy is produced at the end, and so the system basically does a gravitational wave burp that propagates, travel at the speed of light through the universe, waves a little bit the stars around it, keeps traveling at the speed of light, and then fast forwarding 1.3 billion years ago, it arrived on Earth. So Earth was there waiting, the wave arrived, so the first ripples, and then this is the moment when the final burp arrives, boop, and that lasted 0.2 seconds, okay? So that was the last very, very quick moment, and then it's gone. That wave is still traveling. I don't know where it is by now, okay? So this is a very exaggerated effect. it's true, there are gravitational waves going through us all the time, and we basically surf the waves. So we stretch and we squeeze, that's what the waves do to us. But there's nothing like that, okay? So for me, when that happened, it was 4 a.m. in the morning, I slept very soundly, okay? Because the gravitational wave is a very small effect, okay? Space is very stiff. It takes a huge amount of energy to change by a little bit the curvature of space. So it has to be a very powerful event in astrophysical events, and then the change is really, really tiny. So how do we measure that? Well, there were LIGO enters. So LIGO is an interferometer. What does it mean? It means we're using laser lights and the effect of interference to measure these geometry changes, this stretching and squeezing of space. So what you see here is an aerial view of the LIGO interferometer in Hanford in Washington State. It's out in the desert. We have a twin facility in Louisiana, in the middle of the jungle. The two are identical otherwise. And so we're going to zoom in. I'm going to tell you a little bit how LIGO works. So, so if we zoom here in the corner, oh my gosh, if we zoom in the corner station, which is over here, in there we have a laser, like this beam, that gets split at a semi-reflected mirror and bounces back and forth, travels, and recombine. So I'm going to stop and rerun that. What happened there is the two laser beams travel 4 kilometers, bounce off the mirrors, come back, recombine, and then we set things up in such a way that the two beams cancel each other, okay? The gravitational wave goes through, and what it does is it changes the distance between the mirrors. So let's look at it again. So you see the two beams come back, recombine, and then we look at the light that comes out here as they recombine. So let's zoom in. The laser light is a single frequency wave, and so here is the two beams that come back. Sorry, they travel to the mirror, bounce off, recombine, and then we tune things in such a way that they cancel each other. So virtually no light comes out because the two cancel, or the peak and the trough cancel. Now, when the gravitational wave comes, these mirrors effectively move, this distances changes, and so the interference pattern changes. And so as the gravitational wave goes through, we get a little bit of light coming out. So that's the phenomenon of interference that's used by looking at this beam here to detect changes in the length of those two arms that are due to the gravitational wave. Okay, so as the Earth wobbled, the mirrors moved. That's the effect. Now, this is also a very exaggerated effect. The effect of the gravitational wave that we found is such that if we take the distance between Earth and Alpha Centauri, which is the closest star, that distance changes by the thickness of one of our hair. So it's a really, really small effect. We cannot use a detector that's that long, of course. Our detectors are 4 kilometers long. So the effect that we want to go after is tiny. It's 1,000 times the size of a nucleus of a nitrogen atom. So I'm going to play a little video here that shows the hydrogen atom. So this is the electron in the hydrogen atom. This is the nucleus of the hydrogen atom. And there's going to be a counter over here that tells you the size that we're looking at. Okay? So we're going after an effect that's much smaller than the size of the hydrogen atom. It's much smaller than the nucleus of an hydrogen atom. It's 1,000 times that size. So we're looking for movements of those mirrors that are that small. And so why didn't we see gravitational wave before? Because this is damn hard to do. Okay? And so it took about 30, 40 years to design, go from the design of the detector to the construction, taking data, upgrades, taking more data, up until we detected our first event. And that's what got the Nobel Prize in Physics this year. So it's a big endeavor. So we are a big collaboration. So these are the logos from all the institutions there are in the LIGO scientific collaboration. There is somewhere in there the ULB logo as well, and I was trying to find it, and I got lost in the mix. I don't even know where my logo is. Oh, it's here. I made it big so that you can see it. So there's 1,200 of us, 100 institutions, 18 countries. And not only that, so we work with, there are other projects similar to LIGO. So in particular, there is a detector called Virgo, and that's in Italy, in Tuscany, beautiful countryside. So they are working with us now. We are taking data together. There will be, in the not too far future, a detector in Japan called Hydra. And then we are working towards a detector in India. So we're putting these detectors in different parts of the world. And I'm going to tell you why in a minute. So back to our binary black hole collision. So this is the 1.3 billion years ago, the smashing of the black holes. This is what the signal looked like in our data. That happened on September 14, 2015. So I want to show you a little bit more about what that data looked like. So this over here, that's the data from the Hanford detector, the one in the desert I showed you before. That's what it saw. There's nothing, we just filtered the data. We took out the low frequency, the high frequency. And this specific wiggle here, this pattern, is characteristic of the merger of two black holes. Okay? It's as the two get closer, they rotate faster and faster. The frequency increases up until the moment of the merge. And so if we track, as a function of time, the frequency of the signal, this is a signal that increases in time like this. We call that a chirp, okay? Like a bird, chirping bird. This is the waveform that numerical relativity, that solving Einstein equation on the supercomputer, told us, look for something like this. And those of us who were used to work with those waveforms, when we saw this data, the first reaction is falling off our chair. Second reaction is, no way, that's too beautiful. Right? Not only that, but in Livingstone, there was exactly the same thing. 7 milliseconds apart. So remember that video of the wave coming and hitting ortho at the same time? The signal has to appear all around Earth, at most, for the two detectors, at most 10 milliseconds apart. And that's what happened. It matched it really nicely. And here's the chirp in Livingstone. Okay, so that's what our data look like. Now, the frequency of this signal is in the audible band. So we can take that signal and plug it in the speaker and just listen to it. But before I do that, I wanted to show you this one. Okay, I got my slides reversed. We have seen many more of that. So I told you our first reaction was not believing in it. We actually did lots of tests, lots of verification. We really believe in that signal, that first signal. We got more. So we got, like a month later, we found a signal that was weaker, but was still like a binary merger alike. We found one on Christmas evening in my time zone. We found another one then, nice Christmas present. Then we stopped taking data. We started taking data in December of 16. We found another one there. This was in June. This was this past August. So we're actually kind of seeing quite a few of these binary collisions of black holes. And these things, there was no proof they existed before. So this is a whole new area of astronomy. We're starting to build a map of black holes. We are seeing them in gravitational waves with our new eyes. And that's pretty spectacular by itself. So now the sound. I told you that you can actually listen to the gravitational wave just by plugging a signal in your speaker. So I'm going to play sounds for this guy and this guy, so you see a difference between the two. Your ear may not recognize the difference, but we do by looking at the actual time series. And I'm going to play them twice, just because they're fun. But also then I'm going to shift the frequency a little bit so you can hear them a little bit better. I'm starting to lose my hearing, I actually played this in my kids' high school class, and they couldn't hear it either because they used too much the earphones. So I'm going to help you shift it so you can hear what it sounds like. Okay, here we go. That was our first one. This was our Christmas event. Play it again. So now we shift the frequency to hear it a little bit better. So these are the chirp that, now we smile at, but when we first heard this, I mean, if you stop and think about it, we had just heard the final yelp of two massive black holes that were going around each other as fast as like a third of the speed of light. They clash, they produce enough energy to be equivalent to 50 times the luminosity of the universe just in 0.2 seconds. And this is what it sounded like. And that was a new way of exploring the universe. That was completely new. So that's pretty beautiful per se, I think. Okay. So that was one. That was a black hole. I promised you neutron stars. Our second breakthrough moment took place this past summer on August 17, 2017. So I showed you, you heard the clean sound of the chirp. Now I'm going to show you what this actually sounded like with the noise of the detector, okay? So listen very carefully because the chirp is going to be at the very end, okay? So this is, it's kind of tricky to hear, but I want to see how many can hear that, so let's see. Yeah, 20 seconds of noise. But this is what normally the LIGO data sounds like. And take a look at this. This is Hanford, Livingston, and Virgo. And you will see here, you see this trace? This is the signal. It was appearing. And it was staying in our frequency band for much longer than before. And then careful. Who heard it? Okay, good, good. You're better than me, I couldn't hear it. Okay, so this is the chirp that appeared in the Hanford data, in the Livingston data. We really didn't see much in Virgo, okay? So one thing you may notice is this is a much longer signal. So the duration of the signal has to do with the frequency of the signal itself in our band, and that's a marker of the fact that these were much smaller objects. These were not black holes, they were neutron stars. So a neutron star, okay, I'm going to talk a little bit more about neutron star, but before I do that, I want to show you what this is once we take away the noise, the pure signal. Because something else happens. What you're going to see here now is, again, down here, the gravitational wave chirp without all the noise business, so you can get a better idea of the last few seconds of the signal. Up here, you're going to see the data that was detected by a completely different instrument. The Fermi satellite is out there and is detecting bursts of gamma ray bursts. These are just electromagnetic flashes. These events were considered to be the most energetic events in the universe. So you're going to see our data here and their data there. And something really spectacular happened on that day. So let's see. So 1.7 seconds after the chirp, the Fermi satellites got a trigger. They saw a flash of gamma radiation. And now this got excited because we never saw a signal this long, so for neutron stars they were so small. So that was exciting per se, but hey, there was a flash of gamma radiation at the same time. And that has been the first time a single catastrophic event in the universe. Now this thing happened 135 million years ago, we know now. So about the time the dinosaurs were roaming Earth, okay, just to give you the scale. Those black holes happened as life was forming on Earth 1.3 billion years ago. This happened while the dinosaurs were on Earth, okay? So that's the scale of how far in the past we're looking. And there was gravitational wave, and there was radiation. For the first time, we see and we hear at the same time, okay? That's a very powerful first thing. So what's a neutron star? Let me do a little parenthesis. A neutron star is a very interesting object. It's a clump of matter, and that's what's left. It's a burned out residual of a supernova. So stars shine by burning their core, so it's radioactive burning of their core. Once they burn out their inside, they collapse. And then what's left is a bunch of neutrons. This very exotic matter that's just mostly neutrons, and it's really, really dense. To give you a sense, a neutron star is a little bit more like 1.3, 1.4 times the mass of the sun, so 30% more than a sun. And it's compressed in an object that has a radius of order of 10 kilometers. So imagine the sun and squishing it within the size of a city. So here for comparison, this is the San Francisco Bay Area, and this is how big a neutron star is compared to that. So it's a very dense object. Okay, so, and these objects, we already knew that they can come together and they collide. They come together and form pairs. Because those produce light. They're not like a black hole. You can see some of the light that's produced around them. And then, so now what we know happens, what we've kind of worked backwards, is that we had two neutron stars that were in spiraling and then collapsed. They produced gravitational waves. But then, as the gravitational wave was produced, there were these beams of lights. Those are the gamma ray bursts that Fermi detected. And then, so let's see if I'm playing this again. I'm going over my time, but this is a pretty video. So you'll see this kind of nuclear explosion happening here with that looks like matter, that purple things. That's basically all those neutrons that are kind of smashing, and then there is an ejection of matter. They hit the gas that was around it, and they produce a series of rapid neutron captures that then produces bigger isotopes, these bigger atoms, that then decay themselves, and then there was all this halo of radiation left behind. This is known as a kilonova, okay? How do we know about that? Well, because we had LIGO, the two LIGO detectors that detected it. Virgo did not detect it, and then there were a number of observatories that were all there and waiting to find it. So let me tell you a little bit more about what happened there. So the first indication of where this object was located came from the Fermi satellite. The Fermi satellite, the Fermi satellite could only say this object is coming from a patch of the sky that's equivalent of 6,000 full moons. That's a pretty big patch in the sky. Information from other satellites allowed us to restrict to this a little bit smaller area. But then LIGO, the two LIGO detectors, could point at a region that was thinner, this kind of banana-shaped feature that was thinner. And then Virgo didn't see anything. But that was important to know, because we knew that something that powerful would have been seen by Virgo, except it could have been in a blind spot. So knowing that this event was coming from a blind spot for Virgo allowed us to reduce the error region to this. And this is about 140 moons, which is better than 6,000 moons. And just to give you an idea, if you take your fingers, your hand, and you put it up and point at the sky, that's about as big a swath of the sky that was. Okay, so that gives you a sense. So once we knew that, we alerted all of the observatories that we had agreement with. So a bunch of telescopes pointed and looked at that region and started exploring it. And what they found is that they could identify in this patch 50 galaxies where the signal could have come from. And within 10 hours, the Magellan telescope that's in Chile pointed down to this one galaxy, NGC 4933, and they saw a blip of light that was not there the day before. So for the first time, they saw this one transient. And then other telescopes saw the same thing. Here. So all these other telescopes saw within the hour the same object. And so then all of the other observatories pointed toward that location, and that's where the electromagnetic campaign started. And so over the course of 2 weeks, this event that has been the most observed astrophysical event in human history, I believe, was observed by about 80 different observatories, and we got information through all the electromagnetic spectrum. And that's how we could reconstruct that story in the video I showed you before. So, for the first time, we had association between a binary neutron star merger in gravitational wave the gamma ray burst. So this is the first explanation for where the gamma ray bursts are coming from, that specific type of gamma ray burst. And then the kilonova. And so that's a pretty stunning thing. So this event was observed over time. So like the next day, it got dimmer and the light became more red. So for those of you who are passionate about astronomy, you will see this is a spectrum of the light that was detected in the optical. And so over time, the signal became dimmer and this blue bump went away, so it was redder. And what does that mean? Well, simulation tells us that that's the kind of pattern that's due to this radiation that's coming from the production of heavy elements in the surroundings of the neutron star. So now, what we believe, based on the analysis of the optical data, is that these neutrons produced radioactive isotopes that then decayed. We see the light through the decay, and by doing so, they leave behind precious elements, gold, platinum, and other heavy elements like lead. So we now believe events like this have been scattering, producing the periodic table of elements all around the universe, and that's something that happened, we think, in our galaxy as well, because one event like this would be enough to explain the quantity of gold, platinum, lead, heavy elements we have on Earth as well. So I promise you that by bringing together the electromagnetic and the gravitational wave, we would know more. We do. We're now starting to explain where the periodic table came from. And that's a pretty powerful new piece of information. So we're going to go after more of this. So right now we're not taking data. We're improving our detector. But with these informations together, we're really aiming at doing gravitational wave cosmology and chemistry and archaeology, if you want. Okay, it's a whole new potential for new information that we're finding. And we're not doing it alone. We're working with astronomers, with neutrinos. At some point, we may be able to find some of those particles as well that are coming in coincidence with the electromagnetic and the gravitational wave. That would be another sense. So we're really heading towards a multi-sensory experience of the universe, where now powerful astrophysical events, like this, we get the light, we get the particle, we understand the waving of space-time, and that's going to be a new era for astrophysics. So that's what's exciting. That's what really has been powering us. So this is where we started, and our new vision of the universe is going to be more like this. Maybe at some point we will find out what happened in the initial instance after the Big Bang as well. So stay tuned, and I hope to be able to come back and tell you more about that in the next few years. Thank you.